Hello, everybody. Today we have Thies van de Ven. He's a software engineer and software quality expert at Alliander with a passion for teaching fundamentals and helping others. In his talk, Thies will explore effective problem solving in software engineering, showing how understanding core concepts like state management can help developers tackle both modern and traditional programming challenges. Big applause.
Yeah. Hello, everyone. It's good to be back. This is my third year HeapCon in a row. Absolutely love this conference. Me and my friends here were actually at a different Dutch conference yesterday, and we flew in here last night just so we could experience HeapCon a bit. So first, a bit about myself. So indeed, my name is Thies van de Ven. I'm a software quality expert at a company called Alliander, which is a Dutch power grid operator. And as a software quality expert, I get to help a lot of people improve the quality of their code, which is pretty cool. And I also get to call myself expert, which is a pretty neat bonus. I'm also big on knowledge sharing, things like doing conferences like this, or also try to help local meetups a lot, try to organize a lot of things at my job for knowledge sharing sessions. And I basically have been coaching juniors for the past 10 years. So talking about knowledge sharing, let's try to do that today. So we're going to talk about problem solving, standard problems, how to apply those, and how to improve. So problem solving. Why is this something we need to talk about? Well, problem solving is basically at the core of what we do as software engineers. This is the thing that drives us, that makes us excited. We all remember that one thing, we built a feature that you just couldn't finish anymore, and finally things compiled and it actually worked. That's the dopamine you get from problem solving. Or if you spent hours on working out how this bug could be solved, and finally you found it, maybe thanks to OpenTelemetry. That's the dopamine you get from problem solving. So if we do problem solving in our day-to-day lives, we might as well get good at it. So I started looking at ways to improve my problem solving capabilities. And one thing I found was this book, How to Solve It, by George Polya. And this was a mathematician who teaches classes, and this is basically a book on how to solve things and how to explain those things to students. So it's mostly mathematical, but I try to figure out a bit of ways to how can we relate this to software engineering and things that worked for me. So in this book, he promised a way to solve all problems in the world in just 4 easy steps, which sounds quite ambitious, but that's because he cut a few corners. The 4 steps are basically understand the problem, make a plan, carry out the plan, and looking back. Yeah, it cut a few corners, but these are the things that you need to do to indeed solve every problem. And today I want to mostly focus on the top 2, because a lot of people tend to rush in and just write code. They tend to skip the first 2 steps. And the first 2 steps, these are the things that make things easier. These are actually also the things that make things fun. These are also the things that make sure that we write things the right way in the first time. So let's explore how we can get better at understanding the problem and making a plan. Because if you have a good plan, carrying out the plan, that's the easy bit. So in order to understand the problem, a good method to do that is blackboxing. We basically write down a problem like this. You have some input, we have our program, and we have some output. And this basically encompasses all problems out there. So first, we should figure out what our output is. In a lot of cases, we need to do some database calls, or we do some REST service calls, or we have some algorithms. And my screen is flickering, so I hope things will go okay. So all these things need data. So a good thing to start is by figuring out what data do I need to solve my problem. And once we have a bunch of data, we can group these needs together in something that we call types. So first thing we want to do is figure out what types do we need to solve our problem. And once we figure out what those types are, we can figure out what types we need in our whole application. Because once we're done blackboxing, we can try to figure out what steps we need to solve our problem. So given our input, program, output again, what we can now do is split the problem into 2 smaller problems. So we have some input, we parse it, creating parsed input, that feeds into logic, creating output. Notice I gave a name to the in-between state transition. So this is what we call that. It's a state transition. It goes from input to parsed input. And logic takes a parsed input and moves to output. And we can keep on splitting this problem. Like a logic probably needs to get something of a database or something. It needs data enriched. So that takes parsed input as an input, enrich it, creating a rich input, which feeds into logic again, which feeds into output. And if we use this method, by splitting up the problems and assigning a name to every state in between, now we get a very abstract view on what we're trying to do. Basically, we're starting to think in state transitions. In order to solve my problem, I have an input, I need to turn it into parsed input, given parsed input, I turn it into a rich input, and given a rich input, I turn that into output. And this is basically the method I use to solve the complex problems. And this method has quite a lot of advantages. First of all, it's very abstract. We think about what we're trying to do, instead of thinking on how we want to do it. We're only thinking in state changes. Given this, I can create that. Given that, I can create the next thing. And notice how we also don't mention which frameworks we're going to use, how many microservices we're going to use, which programming language we're going to use. We're just focusing on what steps do I need to solve my problem. And all the rest is just implementation details. We also modularize the problem this way. So we build it up into separate steps. And the nice thing about this is, first of all, we can choose where we start solving the problem. Because some problems work quite neatly, going from input, what's the next step, what's the next step, what's the next step. But some problems work better the other way around. That if you have some output, what would be the logical step that would need to precede that? Chess masters, for example, use this all the time. Instead of having a current board position and try to figure out how can I win from this, well, those are millions of paths, so that's a lot of information to process. Instead, they think about what are winning board positions and how can I work my way back to my current position, which is way easier. So thinking in these state transitions, you can either go from left to right or from right to left, whatever fits your problem. It also allows for local reasoning, and this is more on the implementing side. Because if we think in state transitions, you don't have to think about the rest of the software when you're trying to implement one. You just have to figure out how can I get from this state to that state. And the rest of the software, you don't have to think about it right now. So it can also help in implementing this. But most importantly, if we split our problem up enough, the bottom leaves tend to be something I like to call standard problems. So standard problems are problems that have names. And this is something I underestimated for a long time. That once you know the name of a problem, that's an incredibly powerful thing. Because, first of all, if you have to think about software, you tend to have a solution that, oh yeah, it was something like that, and then you have to do something like that and such. There's this whole concept you have to keep in your head. But if you have a name for that concept, you can just think in terms of that name. Your brain can take a shortcut. And that's the whole thing here. We're trying to solve complex problems. So we don't want to have the whole solution in our heads. That doesn't fit, or else it wouldn't be a complex problem. So by knowing the names of problems, our brain can just short circuit. As in, for example, we can fix this using map filter. And hey, now you don't have to think about the whole thing. You just think in terms of the names of the problems. The other nice thing is that once a problem is a standard problem and therefore has a name, there's often a standard solution. So it can also instantly help you with that you already know it. But it can also help you with, for example, if you recognize a problem as a traveling salesman problem, yeah, you might not know how to implement that, but at least you know what to Google, or these days ask ChatGPT to solve for you. But it can also help you solve problems that were similar to the ones you're facing now. Like, even though you don't know how to solve the current problem, you can use this to draw from experience. To give an example, I'm quite relatively new to AWS, never had a lot of experience with that, but I did have to help debug an application. I do have a lot of experience in Kubernetes OpenShift. So in Kubernetes OpenShift, you still have an ingress, a load balancer, and then you have your pod. AWS, it's not exactly the same, but conceptually, it's pretty similar. I can use knowledge from one area and apply it to the other. And because I know the names of the problems I'm trying to solve, for ingress, load balancer, pod, then I know what to Google when solving things from AWS. So knowing the name of a problem is an incredibly powerful thing. So what are some examples of standard problems that we face? What are things that we can expect on those leaves? And what are some things that we can give standard names? First of all, there are just things as simple as things in a standard library. Map, filter, grouping, all these things that you use on a day-to-day basis. These are basically problems which have a name. At some point, I also found this image that mocks functional programmers, saying that, oh, functional programmers have this map, filter, flatten, flat map, and such. We object-oriented programs, we just have a for loop. That solves everything, right? And while that's true, all the problems that for loop is trying to solve, those are problems that have names. If you're trying to do a map thing, it's still called map. That problem is still called map. You can implement it using a for loop, but the problem is still called map. So this is why, in my experience, functional programmers are a bit better in knowing the names for problems and can also break down problems better because they have to know the names of these things. And in the end, again, they can implement them using a for loop, but they will think in, I have to do a map filter. And then it's choice of streaming API or for loop. Another area of standard names are things like design patterns. We've probably all heard about these things like strategy, singleton, or builder pattern. One short note about patterns, you do have to be careful just when you choose to apply those, because some patterns are just missing language features, like the builder pattern, that tends to make up for not having default names, default parameters, and named arguments, things like Kotlin and Scala have. So you don't need to use every pattern in every situation. But it's also an example on how you can communicate about certain solutions through its names. If you go to another program and just say, oh, just use strategy to solve this, you instantly communicate a lot of information just by one word, strategy pattern. So again, learning names for things is very powerful. Then there are things like, things are not, hopefully also a standard problem that you can fix. There are also things like algorithms. Those have names as well, things like shortest path, sorting algorithms. For example, in my company, Alliander, we have a Dutch power grid, which is basically a graph of all the power lines within the Netherlands. So a lot of problems they tend to solve tend to be graph-related problems. And once you know the name of that problem, now suddenly you can look for the optimal solution for that problem, instead of having to figure something out yourself. Or if you use vector databases or something, don't try to come up with some algorithm to solve things yourself. There are named algorithms that are proven to be optimal for certain use cases. And lastly, we have my favorite, my fundamental problems. I can get quite passionate about these. Yeah. And the two fundamental problems within software engineering are state management and side effect management. And these are the things I basically use to do my job. If I look for other people's code, these are the things that I use to base conclusions on, to find certain patterns in there, and to really try to help the team improve. So I want to go a bit into those things, because I use these literally on a day-to-day basis. So state management is important because state is very dangerous. Almost all bugs you ever had come from state in one way or another. Things like race conditions, or you maybe ever had something that you change something here and now something here breaks. That's probably state. Maybe you heard about the expression, have you tried turning it off and on again? Well, what happens if you try to turn it off? All the state gets deleted. And when you turn it on, it has fresh state again. So if something can be fixed by turning it off and on again, it's probably a state-related issue. But state also causes a lot of cognitive load in the brain. So again, if you try to solve complex problems, we need to make it as easy as possible for our brain. And state can cause a lot of adds a lot of complexity to that. To give a short example of that, if I have a function that takes a mutable object as an input, so it has getters and setters, if we print out the car, we pass it to the paint method, and we print out the car again. Do these two things print out the same thing? The answer is, we don't know. It really depends on what that paint method does. Does it make a painting of a car? Or does it paint the car? Does it change its color? And the only way to know this is if we look in the body of the paint and just hope there's not a whole function chain all the way down just to figure out what this bit of code does. If you make a small adjustment and just turn this into an immutable car as an input, do these two print out statements print out the same thing? Obviously, they have to print out the same thing. The car is immutable. That paint method can't change it. So this is how immutable states can directly affect our cognitive load. Before, we had to know a whole part of our application just to figure out what was going on. And right now, we can instantly say something about this bit of code. And so immutability is one of the ways to solve the complexity that state brings. Another thing is the statement that illegal state should not be representable. This basically means that objects should be created in a legal state, which means all the things should be passed to a constructor, and everything should be in the correct state. As in, usually that means no nullable fields, all integers should be positive, that kind of thing. And then we should prevent people from turning it back into an illegal state, which means the easiest way to do that is just use immutability. Then it can't change anymore. And if we do this over and over and over again, we will finally see that all the validation, it still needs to be there, but it slowly moves to the edges of our application. And we will see that we get trusted domain objects that will be pushed into a business logic layer. So instead of a request object instantly going into your business layer, we first do validation, and only if it's correct, turn it to an immutable object, and then pass it to the business layer. So this is how we can deal with state and have to reason about state. So what about side effect management? This is all about pure functions and side effects. So a function can be called pure if it has these three properties. It's idempotent, it's total, and it's referentially transparent. So idempotency just means you can repeatedly call it. And given the same arguments, you always get back the same result. Even if that result is an exception, as long as it's consistently the same exception, then it's idempotent. Total just means that for every possible input, you have to have a valid output, which means exceptions are no longer allowed. And referentially transparency basically just means the function shouldn't do anything outside the function scope. So it shouldn't touch mutable variables from outside of function scope or read something from outside of function scope. Everything should be within the function body. And if we have that, that's pure functions. So side effects are all the things that make functions not pure. Very common things are all kinds of I/O, reading and writing to files, calling a web service, calling a database. These all basically break the previous three rules. They all do things outside function scope. They're all things that can fail. They're all things that might not be repeatable. Also things like combinations of getters and setters. If you have mutable state, those change things outside of function scope. Same with logging. Although logging is usually the side effect that most people are okay with. And these side effects, these are the things that cause trouble. These are also the things that cause cognitive load and also make things difficult to test. If we have this method, for example, that calculates the amount of seconds between now and the time we are passing. So first we carry the current date, then we calculate the amount of seconds, and then we return that. How would you test this method? Pretty difficult, right? Luckily these days, with the modern datetime API, we can actually do this. But it's the first line that gets in the way, right? The current time. And this is how we have to think about side effects. Side effects are implicit inputs into our function. So in this case, time is an implicit input into our function. It comes from outside of the function. And logically, the way to fix this is instead of making it an explicit input, or instead of an implicit input, make it an explicit input. Just pass it as an argument. And now this method is very easy to test. It also doesn't do much anymore. But it is easy to test. And it's now also a pure function. And this is, again, how we think about side effects, implicit inputs into our function. The same, you have the same thing when trying to read a file. The implicit input when you're reading a file is the file system. Because that, if your function signature would be given this file and this file system, yeah, then it would always succeed. But because we don't pass the file system, yeah, that's where the weird stuff is coming from. But we still need these side effects, because we just did an easy thing, just move the side effect up one function, and now it's solved, right? Well, we still need those side effects to happen. So we can deal with it by at least choosing where they take place. If we have a bit of code here that gets used from a database, which is a side effect, then it does some business logic, and then it stores the user in the database again, which is a side effect. So it's difficult to test this code, but what we can do is move our side effects from the business logic. And now at least the side effect, or the business logic can be tested without side effects. So we can't get rid of side effects, but at least we can choose where they take place. And this is usually the point where a lot of people are, yeah, I kind of already knew that stuff. Because I have a whole talk that goes much deeper into all these fundamentals. But I know a lot of people don't really get how powerful these fundamentals are. I use these things a lot to reason about more complex problems. And I want to give you 3 examples to hopefully inspire you to spend more time learning the fundamentals of software engineering. For example, so how can we apply these things? I also already mentioned I coach a lot of students. Every company I went to, I always rounded up the juniors and start to help them. And the nice thing about juniors is they ask questions. They ask why. So at some point, someone asked me, so what's the singleton pattern? So I explained, oh, that's only when you have one instance of an object. But then that person asked, so why would you want that? It's interesting, right? I never actually thought about that consciously. So I never want to disappoint someone. I always want to give a good answer, so I started reasoning. Why would you want one instance of an object? Because if my singleton would look like this, it's just a class with a plus method in it. Would it matter if there's only one instance of it or a million instances? Aside from performance reasons, it doesn't really matter, right? If, however, a singleton would look something like this, where it would get a number from configuration, and that would be the second operand, well, we might want to make this a singleton, right? Because on application startup, it would create this. If we then change the configuration and then another instance would be created, those 2 instances would have different behavior. So now it matters which of the 2 instances I'm getting. So the reason we want only one instance of an object is because we're trying to solve a state-related problem. This thing is stateful. That thing is not. And this doesn't only have to manage state it has itself. For example, if you want to read or write to a file, you might want to synchronize on it. So singletons can be useful for that as well, but then it's managing outside of the state outside of the function. So this is how I could explain things to the student just by using my fundamental knowledge about state management. With my previous company, I also did a lot of interviews. And we tend to ask people to build 2 web services and make them communicate with each other. And you can use any language and framework. And at some point, I got a candidate who used Micronauts. And this was his first time using Micronauts. He thought, oh, this is a good way to try out new things. So that's already a plus. And then I noticed that the beans communicated through static calls. And asked him, so why do you use static for that? Hoping to hear the words dependency injection. But then he started with, oh, I know static is the root of all evil. Oh, that's quite a bold statement, right? I mean, basically every programming language out there supports static. If that would be the root of all evil, then why do all the programming languages support it? So I asked him, so why is this the root of all evil? He said, oh yeah, that's because you can't mock things. Well, when would you like to mock things? If we have our plus function again, would we ever want to mock that? Probably not. If we have a function that, given a file name, gets its extension, we probably don't want to mock that either. If we have a function that, given an ID, gets a person from a database, yeah, that's something we kind of want to mock, right? So what's different, what makes that function different from the other two? The bottom one has a side effect, and the top two are pure functions. And this makes sense, right? Because what are the things that we tend to want to mock? We want to mock things that can fail, that cause inconsistencies in our system. Those are the things that we want to mock. So that doesn't mean that static is the root of all evil. Just using static for side effects is the root of all evil. Stop doing that. But for all the pure functions, in general, you can just use static for that. So again, if you know about side effect management, you can know how to apply static in the correct way. And the last example I want to give is about hexagonal architectures, or onion architectures, or pipe and adapters. It has different names. So this architecture has been existing for quite some time. It more recently got a bit more popular. But I think I've been using this for about 8 years now. And I only learned about its existence about 3 years ago. So how come I've been using it for 8 years now? Well, if you think about it, what does it try to do? It tries to put all the side effects to the edges. Database, web service calls, these are around the edges of our application. So it tries to do side effect management. It chooses where the side effects takes place. It usually, then when it calls a side effect, does all kind of validation and error handling and anti-corrupting layer, and only if everything is correct, puts it into an immutable object and gives it to the domain layer. That's just state management. So if you know state management, and if you do side effect management correctly, you automatically end up with something close to a hexagonal architecture. Again, investing time in learning these fundamentals allows you to understand many, many more complex subjects. So how can we improve upon these things? Well, unfortunately, there's no easy answer. You have to do, how to improve on anything is just practice. So what are things that we can practice? Well, there are two things we can build upon. First, in building heuristics. This is basically extending your standard names vocabulary. So learning more, have a broader experience, learning more standard names. Things you could do is try to learn another programming language. Like I learned a lot about Java by doing Kotlin, and I learned a lot about Kotlin by doing Scala. I might learn something about Kotlin using C#. Who knows? Trying different frameworks. Things like if you use Spring Boot, maybe try Quarkus, maybe try Micronaut, and then figure out what are the things that they have in common. But also figure out what are the things that they do differently, and maybe what are the names for those problems. If you want to get better at algorithms, who here knows about Advent of Code? Okay, if you want to have a really fun way to learn algorithms, it's starting quite soon. Just join Advent of Code. It's a nice coding competition. It's all friendly, and basically, it's all algorithms. Every problem you see, there's probably some known algorithm behind it, and if you can spot it and know the name for it, it's quite a lot easier to solve. Or you can do things like programming katas and such. And for building understanding, there are two things that I use on the, again, I usually try to find ways in day-to-day basis that I can use to learn these things. So things that help me build understanding are debugging and teaching. So debugging is very big on the understanding the problem side, because you have to figure out where the problem is. Also, if you do a lot of debugging, you automatically get quite good at state management. Because, like I said, almost all bugs out there are in one way or another related to state. And ways to get good at that is, if you have a null pointer at a line, maybe don't just put an if statement around it. Maybe find out why was that null there in the first place. And if you have that way of thought in mind, yeah, then you will get quite good at state management. Also, what a lot of people do is trying to look back. Every time I ever solved a problem, I went back through all my steps, figuring out what steps did I do that were successful, what things did I do that were not successful. And by looking back at those and reflecting every time I solved a bug, I actually got quite good at debugging. But my absolute best way to improve my fundamental knowledge was teaching. By having all the junior students ask questions. Because at some point, it becomes difficult to ask yourself the question, why? Why do you do that? Why do you do that? So the obvious answer is, get other people to ask why for you. And this is what the juniors do. They keep asking why. And if they ask something why, I get to, first of all, to see where are the gaps in my knowledge. Some things I can easily explain. Other things are like, I never really thought about that. And then either I don't know, or I can reason it out on the spot, using mostly my fundamental knowledge. Which means that that thing, before, it was just unconscious knowledge, and now it's conscious knowledge. I actually thought about it, reasoned it out now, and now I can use it way more effective. So teaching is actually one of the best ways to learn about getting a deep understanding in how things work. I'm also not the only one who said that, because in doing research for this talk, I found out there's this physicist called Feynman who actually did that. He had very, very difficult physics problems, and the way he tried to figure those out was to just keep on explaining the problem to people and using them to ask why, so then he could figure it out. And I just want to share this because I thought it was a bit ironic that I have a whole talk talking about standard problems, and the one thing I've been doing for the past 10 years turns out to be a standard problem called the Feynman technique. And with that, we're getting out of time. So in conclusion, we learned how to solve any problem by just using these 4 steps. We learned how to think in state changes as an abstraction of a problem. We learned the value of standard problems, and most importantly, the fundamental problems. And we learned that one of the best ways to improve our understanding on this is by sharing knowledge. And helping yourself by helping others is, I think, one of the most beautiful things. And with that, I'm going to end this talk now. If you have questions about this or just want to talk about functional programming, programming in general, I'm quite passionate about that. Feel free to come to me. I'm here all day. You can find slides, recordings and everything from previous sessions on my website. And if you want to chat a bit on chat, just add me on LinkedIn. And with that, I would like to thank you so much for having me back at HeapCon, and I hope you have a great day.